Okay, this is going to be a recording. Just needed to shut the door. And I'm going to start the camera up here. Okay, so we're filming. All right, hello. This is going to be a brief introduction to using the Nova Nanolab for SEM imaging. I'm going to walk you through the basic procedures of loading a sample, turning on the electron beam, optimizing image parameters, taking a few test images, and then we'll shut the system down and safely remove our sample so that the system is ready for the next user. When we sit on the Nova Nanolab, the user interface is composed of several key areas. We have 4 different quadrants that display different images from the microscope. For example, quadrant 1 can show the SEM image, quadrant 2 can show the FIB image, and quadrant 4 can show the CCD camera image. There is a toolbar of icons across the top of the screen. These are shortcut icons that allow you to easily access parameters on the microscope, such as accelerating voltage, beam current, reduced area scanning mode, scan speeds, and image resolution, and etc. There is a panel of functions on the right-hand side of the user interface that contains many of the other functions and parameters that need to be changed on the microscope. The right-hand panel is subdivided into 7 distinct tabs. Each tab has a name. For example, the first tab is called Beam Control. The second tab is Navigation. Underneath each one of these tabs are going to be certain parameters that are categorized according to the tab name. So for example, in the Navigation tab, we have the ability to control the stage coordinates and move the stage around to position the samples underneath the electron beam. There is a patterning tab for controlling depositions and milling with the FIB. The 4th tab is the image processing tab. The 5th tab is the detector tab, which allows you to change between the various detectors on the tool. The 6th tab is called sample prep, which combines some of the features from the navigation tab and patterning tab together, as well as the scan rotation from the beam control. And then finally, the alignments tab. Now, as a new user, you should not need to go into any of the functions in the alignments tab. These are mainly going to be for the tool manager to operate. Now, when you first sit down on a microscope like the Nova, you will generally find that it is under high vacuum. We leave the systems under vacuum in order to keep the chambers clean and maximize the imaging potential of the system. The vacuum status of the microscope can be viewed by going to the bottom right of the user interface, where we can see that the chamber pressure is currently 6.76 times 10 to the minus 6 torr. And we can see that the 3 main areas of this little icon are all bright green. If one of these icons were orange or gray, it would mean that that component of the microscope was vented to atmosphere, which could potentially be a problem. So to load our sample, the first thing we need to do is to vent the microscope. The vacuum controls are located in the beam control tab at the top where it says vacuum. There is a button to pump and a button to vent the chamber. We're simply going to take the mouse and click on the vent button. The software will ask us, are you sure you want to vent? And we can say yes. The Nova Nanolab takes around 4 minutes to vent. I'm going to speed up the video so that you don't have to wait for all of this. But keep in mind that there is a few minutes of wait time once you hit the vent button. If you need to get your sample ready to load, this would be an excellent time to do that. Otherwise, you just have to sit and wait. Now, since we've hit the vent button, the system is starting the automatic venting procedure. You will notice that the chamber icon in the lower right has now turned orange. Orange indicates that the system is changing condition, in this case venting. Once we've loaded our sample and hit the pump button, you will see that the chamber icon turns orange again to indicate that it is pumping. And once it turns bright green, we will be at high vacuum and we can turn the electron beam on and start imaging. But I'm getting ahead of myself. For now, we're simply going to wait for the chamber to vent and then we'll load the sample. Now, nothing in this software will tell us when the chamber is fully vented. This icon will change to gray after a fixed amount of time has passed. However, we don't have to wait that long. As soon as we can open the door on the microscope, we can feel free to go ahead and load our sample. We don't need to wait for this to change color, but it will eventually based on the specific timeout parameter on your specific microscope. I believe on the Nova it is set to a 5-minute wait. So at this point, I'm going to reposition the camera and the microphone over by the door of the microscope so that we can see what we're doing when we load the sample. Okay, so the chamber is fully vented, and the way that I can tell that is by simply taking my hand and gently pulling on the door. And if the microscope door rolls open, then we know that the chamber is vented and we can go ahead and load our sample. If the door does not open, then the chamber is still partially under vacuum and we need to wait a little bit longer. When you open the microscope door, it is important that you do not let the door crash against its stop. The door can slowly be opened until the handle approximately reaches the end of the counter. At this point, you will feel the door hit a stop, and you should not pull any more than that. If you pull the door rapidly open and crash against the stop, it can actually shake components loose on the microscope stage, which could cause service issues for the system. Now, everything inside the microscope chamber is an extremely clean environment. It is important that we do not touch anything inside the vacuum chamber with our bare hands. We always want to put on a clean pair of nitrile gloves before touching anything inside the vacuum or before touching our samples. So in this case, my samples are in protective plastic cases, but the second that I'm going to open these and load them into the microscope, I need to make sure that I do not touch the samples with bare hands either. So the samples need to stay clean, the inside of the microscope needs to stay clean, otherwise we will have a lot of contamination problems to deal with. So I'm going to go put on gloves. We always keep gloves by the microscopes, so you should be able to readily find new clean gloves. If for some reason one of the boxes has run out, contact one of the staff and we will find more. We want to always keep the systems clean. Okay, so I have on my clean pair of gloves, so now I can safely touch the components in the microscope, the stage, or my sample. So let's talk a little bit about this stage design. The stage on the Nova is connected to the chamber door, so when we open the door, the stage moves with it. This is a 5-axis stage that allows us to move in X, Y, Z, tilt, and rotation. In order to hold on to our samples, we need to use a stage adapter, which is screwed into the rotation plate of the stage. Now the stage adapters are removable and they are height adjustable. We have two different adapters that are commonly used in our facility for this microscope. The adapter that is on the stage right now can hold up to 5 small SEM stubs at a single time. The other adapter can hold a single SEM stub. Let me get this to focus. Can hold a single SEM stub. Now, both of these adapters have a similar design. They have, let me get this to focus better. Okay. So there is a long threaded bolt that screws into the stage plate, and this is used to adjust the height of the adapter. After the height is fixed, I'm having trouble with my focus here. After the height is fixed, this cone nut can be turned down to secure the adapter against the rotation plate of the stage. This locks everything into position. So I'm going to demonstrate this by loading my samples onto the 5-stub adapter. Okay. So the first operation will be to loosen the locking nut. Usually the last user has left this tight. So we're simply going to pinch the locking nut with 2 fingers and turn counterclockwise, and that should loosen it. If for some reason the last user has over-tightened the locking cone nut, you may have to grab onto the rotation plate with one hand to keep this from spinning and loosen the cone nut with the other hand. But that is not a typical situation. So once the cone nut is loose, we can now spin the stage adapter to any position that we want. This is useful because it allows us to access the small 1.5 millimeter set screws on the perimeter of the holder, which are used to secure the samples. So the first sample I'm going to place on the stage is a simple alignment sample that we use for maintenance purposes on the dual beams. It has a variety of materials on it, and I can simply put the small stub on the bottom of the sample holder. You can see it anyway. There's a small pin that sticks out the bottom, and that just simply drops into one of these holes. So I can put this onto the stage, and then my second sample I will position on one of the other spots on the stage adapter, like this. Now, before I secure these samples, I'm going to change the camera angle a little bit here. It's important that we get the surface of each sample into the same plane. So let me drop this camera down a little bit, and I'll show you what I mean. If I rotate this slightly. Right. Now, these two samples have different heights. The sample on the left, I should point with this wrench here, the sample on the left is approximately 1 millimeter taller than the sample on the right. Now, in order for us to load these samples safely, we need to get them at the same height. Now, I cannot shorten the sample on the left, but I can raise the sample on the right up before I tighten the set screw. So what I'm going to do is carefully raise up this sample slightly and then tighten the set screw. And then I will double check the height and confirm that I have now gotten the two samples at approximately the same height. Okay, so both samples are now secure. They're approximately at the same height. You should strive to position the samples within 1 millimeter height difference or less of each other. This should not be too much trouble. If you cannot get the samples within 1 millimeter height difference, then you should load one sample at a time. It can be very hazardous, especially if you're going to tilt the microscope stage to have different heights in the chamber at the same time. Now that we have both of our samples on the stage adapter and secured, we next have to adjust the height of the adapter. So I can make the adapter taller or shorter by turning it either clockwise to make it shorter or counterclockwise to make it taller. In order to determine the correct height, we need to use the height gauge. Now the height gauge should always be sitting next to the microscope, and the gauge is set onto the stage next to the samples. Now the gauge has a couple key components to it. There is a nose of the gauge with a 5 line pointing at it. If your samples are exactly at this height, they will be 5 millimeters away from the bottom of the lens when you close the door. If your samples are very, very short, they will not have, you will not have the ability to raise the stage up to get to the appropriate working distance. This is shown by this lower edge here. So the samples must be between these two positions. You must be shorter than the 5 line, and you must be taller than this lower edge. Beyond those constraints, there isn't a very specific height that you need to load a sample on this microscope. Anywhere in this whole range is okay. Practically speaking, I like to aim for about 2 to 3 millimeters below the 5 line. I find that's a very useful distance to start at. It allows a lot of flexibility and allows a lot of safety when you close the door. The very top surface of the gauge has a 1 pointing at it. This surface is only 1 millimeter away from the bottom of the lens when you close the door. It is imperative that you never ever have a sample taller than that surface. If you do, when you close the door, it will hit the lens, and that causes significant damage to this microscope, on the order of $20,000 to $30,000 to replace the SEM lens. So it is absolutely essential that you make sure that all samples are lower than the 5 millimeter line. Now, where I have the sample right now is okay. We can see that the larger stub is about 1.5 millimeters below the 5 line. And if I check my second sample, I can see that that is also about 1 millimeter below the 5 line. So I should be okay to lock the stage down. Now if I need to adjust this, I can go clockwise and make it slightly shorter. I can go counterclockwise and make it slightly taller. Let's just double check the height again, and we can see that I have a good clearance below the gauge. So now I will secure the cone nut. Now to tighten the cone nut, I'm just going to pinch it with 2 fingers and turn it clockwise. Maybe use your second hand to prevent your stage adapter from rotating. And I'm just going to secure it like that. We don't want to over tighten the locking cone nut. If you do, it can cause problems for removing your samples later and potentially damage the microscope. So only use enough force to make sure that the stage adapter is held in place. I recommend that after you think it's tight, take your fingers and give a little wiggle test on the stage adapter, and it should feel solid. If you don't have the cone nut tight enough, for example like this, then when you do that wiggle test, you will find that you can cause the stage adapter to move back and forth. This is an indication that you're not tight enough. So go a little bit tighter, give it a wiggle test, and everything feels good. So now we're ready to close the door of the microscope and pump the chamber down. When you do this, it is a good idea to look at the CCD camera on the microscope user interface. The CCD camera will show you when you close the door if you have a sample that is going to potentially hit the lens. So I'm going to, let's lower our mag here a little bit on the one camera. And as I close the door, we'll go back to the CCD camera view. we can see the samples come in from the right-hand side and traverse below the lens. Now, if the samples were too tall, we should be able to determine that we may hit the lens before we actually hit the lens surface. So please be careful and watch the CCD camera as you close the door. Now we're ready to pump the chamber down. So we're going to go to the user interface, and we're going to take the mouse and simply click on the pump button. Now, while the chamber is pumping, you may have to gently push on the door of the microscope to get this chamber to seal. You should not have to push hard, and you should also avoid pushing on the stage feed-through controls. These can be damaged if you push on them, but feel free to push on the flat surfaces of the door or on the handle at the bottom of the door to get the chamber to seal up. Now, this microscope takes around 5 minutes to reach high vacuum, so we have about 5 minutes to wait. I'm going to reposition the cameras again, and we'll meet up again to start imaging. Okay, so we're back, and the chamber has fully pumped down, as indicated by the green icon in the bottom right of the user interface. And we can see that the pressure is now 3.2 times 10 to the minus 6 torr, which is a pretty good vacuum level. Now this chamber has been pumping for about an hour. I went and got my lunch, so the system has been pumping for a little bit longer than what would be typical. But this isn't a bad thing. What we'll find is that we should have less contamination, and we should have better imaging quality because the system is under better vacuum. And so the first thing we want to do is we want to turn on the electron beam. Now, the controls for the beam on are going to be found in the beam control tab on the right-hand panel. However, these controls in the panel and the controls on the toolbar and the controls on the manual user interface, or MUI, are all specific to the quadrant that is selected. In this case, quadrant 4, the CCD camera, is selected. I can tell the active quadrant or selected quadrant based on the color of the data bar. The data bar in quadrant 4 is blue, while the other 3 quadrants have gray data bars. If I take the mouse and click one time in a quadrant, it changes the selection to that active quadrant. Now you should notice that in the panel on the right-hand side, a lot of these buttons become activated when I selected quadrant 2. That is because some of these functions are disabled for the CCD camera and can be changed for the FIB or for the SEM. The way to tell which beam is set in each quadrant is to look at the icon in the lower left corner of the quadrant. The 3 different icons are a light bulb for the CCD camera, an ion nucleus for the focused ion beam microscope, or FIB, and an electron cloud for the SEM. The assignment of the signals on the quadrants can be changed if you want to. This is done by selecting a quadrant and then changing the icon in the top left of the user interface to a different signal. For example, I can choose quadrant 2 and then set this to the what the software calls the optical beam, or as I refer to it, the CCD camera. And then I can hit the pause button in the toolbar to start scanning. I now have 2 identical CCD camera images in quadrant 2 and quadrant 4. If I want to change a quadrant back to the FIB, I'll pause my image and I'll choose the ion beam symbol, and now quadrant 2 is back to the focused ion beam image. The reason you would do this is if you have a microscope that has several types of electron detectors, you may want to image multiple quadrants at the same time. For example, you could have quadrant 1 showing a secondary electron image, and you could have quadrant 2 showing a backscatter electron image. Now, this configuration requires your microscope to have a dedicated backscatter detector, which on our Nova, that is not possible. So normally the Nova Nanolab is set up to only show the SEM image in quadrant 1, the focused ion beam image in quadrant 2, the CCD camera image in quadrant 4. Quadrant 3 can be used for loading images that you acquired on previous sessions. It could be used to load reference images. It could be used to show another version of the CCD camera. Sometimes I've seen users have the CCD camera in both quad 3 and 4, and then they will digitally zoom in on one of the quadrants so that you have a slightly higher magnification view of the CCD camera. But it's up to you what you want to do with quadrant 3. We really don't have any dedicated detector to put here. What I generally do is just leave it as a frozen black screen so that it's less distracting. So we want to turn on the SEM, which requires us to select the SEM quadrant. So when we choose the SEM quadrant, that means that all of the functions in the panel on the right-hand side and all of the toolbar icons, as well as the knobs on the MUI, will all apply to the SEM. I can then go to the column area in the beam control tab, and I can hit beam on. When you push the beam on button, an isolation valve will open, which separates the electron column from the chamber. You should hear that valve open. It's pneumatically operated, and it makes a very distinct sound when it opens. In addition to that valve opening, the acceleration voltage will turn on for the SEM, allowing you to use the microscope. The name of the button is called beam on. This is somewhat misleading for this microscope because the electron emitter on the Nova is always energized. So there is always an electron beam being emitted from that tip. I believe it is a historical reason why FEI chose to use beam on as the name of this button so that this software can apply to other types of microscopes. But keep in mind that you're not actually turning the electron beam on or off, but you are configuring the microscope to allow you to actually image it or use it for imaging. Now, a yellow button means that the beam is on. A gray button means the beam is off. So if I click on the beam on button again, you will see that it turns gray. This indicates that the column isolation valve has closed and the acceleration voltage is off, and I will not be able to use the tool for imaging. This is a common mistake I see with new users, is that they forget to turn the beam on, or they think that the beam is on because this says beam on. But make sure that the button is yellow, otherwise you do not have the ability to actually image with this system. So I'm going to push this again, we'll turn the beam back on, and now we can form an image. Now, just because we have the electron beam enabled doesn't mean that we're going to get a picture on the screen. We have to start our scanning. The scanning is started and stopped using the pause indicator in the toolbar, or by using a keyboard shortcut key. Most of the keyboard shortcuts are located in these drop-down menus at the top of the screen. If I go to the scan menu and select it, I can see that the function for pause is also controlled by the keyboard shortcut F6. So you have a variety of ways of controlling parameters on this microscope. You have keyboard shortcuts, you have toolbar icons, and in some cases you have mouse 2D adjusters and mouse shortcuts. I'll try to mention some of these as we go through the training, but it's going to be up to you to decide which methods you prefer for controlling this microscope. My preference is to take the mouse and simply click on the pause button in the toolbar. So when I hit the pause button, you'll see that the scanning is initiated in quadrant 1. We now have a live image. You may or may not see anything on the screen. For example, if I turn up the magnification a little bit, we now have an image of a black area. This can be frustrating for a new user because they expect to see a picture of their sample when they turn the scanning on. My suggestion for this type of situation is to first lower the magnification of the microscope to the minimum value that it is capable of going to. This can be done in a variety of ways. On the manual user interface, the large knob in the center is the magnification knob. This can be turned clockwise to increase the magnification or counterclockwise to decrease the magnification. We just want to spin the knob counterclockwise until the image stops changing magnification. Another way to change the magnification is there is a mouse slider in the beam control tab right here. I can click this to the right to go higher mag. I can also click in this white area to jump by larger steps, or I can grab the slider and move this left and right to change mag. You can also go up to the drop down in the toolbar and you can choose preset magnifications that are available. Now, the system allows you to go to other magnifications than are in this preset list, but if there's a magnification you want to go to, you can simply select it. However, because we want to go to the lowest possible magnification, I find that the magnification knob on the MUI is by far the easiest way to do this. So again, I will just spin this counterclockwise several times until I see the magnification is at a minimum value. In this case, 37x. Now, you may or may not have an image at this point. If you do not have an image, it is usually that the brightness and contrast of the microscope are not configured correctly. For example, if I lower the brightness and contrast too much, I now am back to my black image where I don't see anything. As long as you're at the lowest magnification, you should always see the inside of the electron lens. So what we want to do now is to adjust the brightness and contrast to try to get our image back. Now there's two ways to adjust the brightness and contrast. You have a contrast and a brightness knob on the manual user interface, or in the beam control tab at the bottom, there are mouse sliders for contrast and brightness. These control the same function as the knob. So if I turn the contrast knob, you can see the contrast number changes in the beam control tab. Same thing with the brightness. There is an auto brightness or auto contrast brightness function in the toolbar, which is the half white, half black circle. If I push this, the software will run the auto contrast brightness function and try to establish good imaging parameters. It is not guaranteed that this will produce a perfect image, but it usually does a good job of getting you a usable image quickly. So feel free to use the auto contrast brightness function. But keep in mind, you'll probably have to make small adjustments to contrast and brightness after you find your sample. And as I mentioned, even if you don't have anything beneath the electron lens, at the lowest magnification on this microscope, you should be able to see the inside of the electron lens, which is this large circular feature surrounding the edges of my image. So if you still cannot see this after going to the lowest magnification and adjusting your brightness and contrast, it probably means that something else is wrong with the microscope. Make sure that your beam is on, as shown by a yellow icon, and also make sure that you have an electron beam actually coming down the column. And by that I mean check your source tilt and your lens alignment, and we'll get into that a little bit later in this tutorial. But if the source tilt is too far off, you may not get an image at all. In this case, we do have an image, so our next procedure is going to be to move the stage to locate our sample. Now, there are a variety of ways to move the stage on the Nova. The first way I'm going to show you is to take the mouse and double click on a feature that you can see. For example, I'm going to double click on the center of this large hole, And by double clicking the mouse, that's the left mouse button, it moves that feature to the middle of the screen. So if I want, I can double click on the right side of the screen and that moves that feature to the center. Here's a little dust particle, I can double click on it and it moves to center. This is a very useful way to move around on the stage, assuming you can see the features that you want to look at. If you have to go a long distance on the stage, moving in this fashion can be rather tedious, but you can walk your way around the stage by double clicking the mouse. A second way to move is to take the mouse and click and hold the left mouse button down and drag a box on the screen, and then let go of the mouse. When you do this, the stage will move to the center of the box and the magnification will adjust to fill the field of view based on the size of your square. For example, I've zoomed in and caused a small contamination mark on this sample holder. If I want to go back to that magnification, I can click and highlight a box surrounding that area and let go, and the magnification will adjust and the stage will move to the center of that area. Keep in mind that this function only allows you to zoom into higher magnification. You cannot go to lower magnification on the Nova by doing this. The only way to go lower magnification would be to use the magnification knob or the drop down or the mag slider in the panel to go back to lower magnification. Another thing to keep in mind is that this function is only enabled if the mouse is showing as a mouse pointer. If you are in the patterning tab or the processing tab and have a pattern selected or a measurement selected, the mouse will be a crosshair. In this case, if I click and drag the mouse, the software thinks I'm trying to draw a shape on the screen instead of moving the stage and changing the magnification. So if you want to move by highlighting a rectangle box, you need to make sure that the patterns are disabled and that the measurements and annotations are disabled so that the mouse appears as a mouse pointer, which will then allow you to drag, click and drag. Now, if you click and drag and create this rectangle box and decide that you don't want the stage to move, there are two ways to get rid of this. If I let go of the mouse right now, the stage will move, which could potentially be a problem. If you shrink the area down until it turns red and then let go of the mouse, the stage will not move. You can also hit the escape key on the keyboard and that will delete the rectangular selection and the stage will not move and the magnification will not change. Another way to move the stage is by pressing down on the mouse wheel in the center of the mouse and holding it down. If I do that, so if I click the wheel, hold it down, you see the mouse becomes a little yellow dot. I can then drag the mouse in some direction and the stage will start moving in that direction. The speed is proportional to how far away the yellow arrow is from the yellow dot. So if I put the arrow very close to the dot, the stage will move rather slowly. If I move the arrow a long way away from the dot, the stage will move quickly. And I can change directions by simply moving the mouse in different orientations on the screen. If I let go of the wheel, the stage will stop. This is a very, very useful feature to move long distances on the stage. The speed is proportional to the distance between the arrow and the dot, but it also changes with magnification. So if I go to the lowest magnification on the system, this will allow me to move extremely fast around the microscope. Now I'm just clicking the wheel and holding it down, and this allows me to then stop the stage by simply letting go of the mouse. You can also double click the wheel down, which then locks the mouse into joystick mode. And now in this case, I don't have to hold the button down. I can simply move the mouse in some direction and cause the stage to move. You need to be a little careful using this because if you forget to turn the mouse back into normal mode and walk away from the tool, the stage will keep moving in some direction until it either runs out of travel or crashes into something. To turn off the joystick mode, simply click the mouse again and everything will stop. An additional way to move the stage is by using the arrow keys on the keyboard. The arrow keys will cause the stage to move by approximately 80% of the field of view in one direction. So if I push the right arrow key, the stage will move by about 80% of its field of view in the direction that I've indicated. If I push the up arrow key, it will move in the up direction. If I push the down, it will move in the down direction. These distances will change with magnification. So if I turn the magnification knob to a higher value and now push the arrow keys, the stage will still move by approximately 80% of the field of view every time I push this. If you're using the arrow keys, keep in mind that the microscope software does not react well to pushing the arrow keys very quickly. If I push the arrow keys multiple times in a row, the stage generally moves just once. If I hold the arrow keys down, the stage will move in a rather chaotic fashion and can be very difficult to actually stop, especially at very low magnification. So I recommend that if you're going to use the arrow keys, push the arrow key and let the stage move, push the arrow key, let the stage move, push the arrow key and let the stage move, and so on. Don't try to push the arrow keys many times in a row. You will not get the expected result. Another way to move the stage is by going to the navigation tab in the panel on the right, and in the navigation tab we can choose the coordinates sub-tab and type in direct stage coordinates. At the moment, my X and Y coordinate are shown as 2.5 and 2.25 millimeters. I can highlight these values and type in a coordinate where I want to go to. So let's go back to 0, 0, and I can click either the go to button here with the mouse, or I can push the enter key on the keyboard. When I do that, the stage will then move back to 0, 0, which puts us approximately in the center of the stage adapter. I can also type in coordinates for the z-axis, the tilt axis, and the rotation axis. Instead of going to direct coordinates, I can also change this drop down to relative coordinates, and now I can move in relative direction and displacement based on where I'm at right now. So in relative mode, if I type in 1 millimeter for delta x and say go to, the stage will then move over 1 millimeter. Now I don't have to type it in again, but if I hit go to, I'll keep moving over 1 millimeter each time. Now you see that this stage sometimes does a backlash correction, which causes it to move in the opposite direction and then back. This is to improve landing accuracy, so don't be surprised if the stage doesn't initially move in the direction you think it will. If I change this back to actual, the drop down back to actual, it shows me my current stage coordinates. The second I type in a new coordinate, you'll see that the drop down switches to target. Target indicates where you will go when you hit the go to button or the enter key. If I don't want the stage to move, I can simply change this back to actual, and then it will reflect my current stage position. The last way to move is there are 4 mechanical knobs mounted on the front of the microscope door. I think I'll start a separate little movie here to show that, or maybe I'll just input a screen capture of the knobs. But the 4 knobs on the door are directly linked to the X, Y, Z, and rotation axes. You can move these axes around by turning the knobs with your fingers. Now you can't see this on camera, but if I go over to the microscope and turn the X knob, you can see that the X coordinate is changing in the software, and we're moving the stage in the X direction. I can also do this with the Y direction and so on, Z and rotation. Generally, it's much easier to use the software to move around, but there are some circumstances where it's better to use the mechanical knobs. For more advanced users that are working with the fib, the Z knob is the easiest way to set the eccentric height on the stage. But again, that is a much more advanced topic than what I want to cover today. So my two preferences for moving around are to double click the mouse on features to move them to center, or to press the wheel down and hold the wheel down and use the mouse as a joystick mode. I find the combination of these two to be very, very efficient. So what I'm going to do is to use the joystick mode, and I'm going to move the stage and try to locate my sample. And all right, here's my sample. Once we locate the sample, the next operation of the microscope is to determine how far apart the sample surface and the bottom of the lens are with respect to each other. This is an extremely important task because it allows the microscope to safely position the sample below the lens and prevents you from crashing samples into the lens surface. Now, the way that we can measure the gap between the lens and the sample is by focusing the microscope on the surface of the sample. In the data bar of my SEM image right now, I have a parameter shown called WD, that stands for working distance. This is a measurement of where the electron beam is focused for its image plane. If I change the focus knob, which is the far right two knobs on the manual user interface, I have a fine and a coarse focus. If I change the focus, I will cause the working distance to change. This simply means the objective lens is changing condition to move the focal point up or down. Now, if the image of the sample surface happens to be in focus, then that number is a very good way to measure the distance. However, it requires the surface of the sample to be in focus. If that image is not in focus, then this number is meaningless. Now, when you focus a scanning electron microscope, it's important to ensure that the magnification is high enough to actually see when you're in focus. In this example, the image on the screen does not look that far out of focus to me, but it's because we're at 36x. If I turn up the magnification to a higher value, we can now see that the surface is actually quite far out of focus. I suggest that new users turn the magnification at a minimum to 2000x. Now you can go higher than this, there's no reason not to, but try to avoid focusing at values lower than 2000x because it's most likely you're going to make a mistake. So if we turn up the magnification to a higher value, in this case we'll go to 2000x, I will then adjust my focus so that the image on the screen looks suitable. Now in this case I'm just going to use the fine knob, but I could use the coarse knob as well. So I'm going to turn the knob clockwise, which causes the focus to go to longer working distance values. If I turn the knob counterclockwise, it causes the focus or working distance to go to smaller values. So as I turn the knob, I see that the image on the screen slowly comes into focus, and when I think I'm at a good focus value, I'm going to stop turning the focus knob. Now again, this can be done with the coarse knob or the fine knob, it's up to you. Now, once I have the image in focus, I want to tell the software to use this value, 7.8 millimeters, as the reference coordinate for the z-axis. Now, what do I mean by that? Let's go look over here in the navigation tab. For the z-axis, the software shows that we are currently at 0 millimeters. Well, practically 0 millimeters. And it shows that the positive z direction is up, as indicated by this little red arrow with the plus sign pointing up. What that means is that if I were to type in a number, say 1 millimeter, and hit go, the stage will simply go up 1 millimeter. This number is independent of the distance between the lens and the sample. This is only based on the raw height of the stage. Now that value is not terribly useful to us as a microscope operator. What we care about is the distance from the lens to the sample. Now, when my SEM is in focus and I know that this value is correct, I am going to then push this icon in the toolbar. It's called Link Z to FWD. and it says not linked. When I push this icon, the software is going to transfer this working distance value to the z-axis, and the positive direction of the z-axis is going to invert. So let's do that and see what happens. So I'm going to push the red question mark icon, link Z. You see the icon changes to a green up and down arrow, indicating that you have established a link between the working distance and the z-axis. And now over here in the z-axis, the value, instead of 0, now reads as the 7.76 value, which came from the working distance. And the positive direction is now shown as down. In the linked coordinate system, 0 millimeters positions the surface of my sample against the lens, and large values move the sample down away from the lens. This is much more useful for a microscope operator to work in this coordinate system instead of the raw stage height. So now I can tell the software to go to any working distance that I want for my imaging. For example, on the Nova, the default working distance is 5 millimeters. So I can type 5 for the z-axis and hit the enter key, and that will cause the stage to move either up or down depending on where it's at, so that your sample is now 5 millimeters away from the lens. Similarly, if I wanted to go to 1 millimeter, I could type in 1 and hit enter, and that would cause the stage to move up so that the sample is only 1 millimeter away from the lens. It's important to keep in mind where your samples are and what is the coordinate system that you're using for the z-axis. It's very easy to crash if you type in the wrong value. So let's go back to 5 and bring the sample back down to 5 millimeters. Now that we've moved the sample to 5, the next thing that we want to do is to choose the acceleration voltage and the beam current for the microscope. The accelerating voltage can be changed in 2 positions on the software. The first is this drop-down menu in the toolbar. This is a list of preset values that you can choose. There's only 7 values here, and there are rather large steps between them. If a voltage exists that you want to use, you can simply select it. For example, if I want to go to 3 kV accelerating voltage, I can choose 3 kV, and the software changes to 3 kV. If I want to go to 10 kV, I can select 10 kV, and so on. If you want to use a voltage that is not available in this preset list, the other position to change the voltage is in the beam control menu in the high voltage area. The high voltage has a couple of buttons to it. The plus and minus button simply move you through the preset list. So if I hit the minus button, the voltage is going to change from 10 kV to 5 kV. And if I hit the minus again, it'll go to 3 kV. If I click on the drop-down arrow, it also shows me the preset voltages. However, if I want to choose an arbitrary voltage, the way to do this is to just click on the number so that it is highlighted, and then I can type in any value that I want. For example, let's go to 65 volts. I'm just picking a number off the top of my head. There's no significance to this, and I hit enter. So we can now go to any voltage that we want. The minimum allowed voltage on the Nova is 300 volts, and the maximum allowed voltage is 30,000 volts, or 30 kV. You cannot exceed those limits, but you are allowed to go to any voltage in between those values, regardless of what is in the preset list. Now, choosing accelerating voltage is one of the harder parameters for new users. If you use an improper accelerating voltage, you will find that your resolution is not as good as it could be, and your image contrast may not be what you expect. This is especially important when you're working with nanoparticles or nano-sized features on the surface of other objects, or working with non-conductive or semiconductor samples, which may charge up. On the Nova, good accelerating voltages generally fall between 1 kV and 10 kV, depending on the type of sample you're imaging. I typically recommend that a new user starts at 5 kV if they don't know anything about their sample or how the microscope will behave. If you're trying to maximize the SEM resolution, I usually recommend that you aim for voltages somewhere between 3 and 8 kV. But again, 5 kV is a very good all-around voltage. After you choose the accelerating voltage, the next parameter to select is the beam current. On the Nova software version that we have, the only place to change beam current is in this drop-down menu on the toolbar. If I click on the beam current list, I can see that I have 7 different beam currents available. The smallest beam current will be at the top of the list, the largest beam current will be at the bottom of the list, and then there are various steps in between. For routine SEM imaging, I generally recommend that you use either the 3rd, the 4th, or the 5th beam currents. I find these work very well for most samples. If you're trying to maximize SEM resolution, you should look at the 1st, the 2nd, or the 3rd beam currents. If you're trying to maximize signal for EDS analysis or for doing depositions with the SEM, I would look at the 5th, 6th, 7th beam current. But again, for routine imaging, stay more towards the middle of the list and you will have a good experience. Now, the numbers shown in this table are calculated based on the lens parameters and the accelerating voltage. So expect that these numbers will change if you make a change to the voltage. For example, at 5 kV, the middle beam current is 0.40 nanoamps. If I change my voltage to 10 kV, the middle beam current is now 0.54 nanoamps. It's similar in magnitude, but again, the numbers will change slightly. For this demonstration, we're going to choose 5 kV accelerating voltage, and we're going to choose 0.40 nanoamp beam current. Now, after you choose your voltage and choose your beam current, the next step of the process is to align the microscope column. There are 2 steps to aligning this column. They're both located in the beam control tab. The first step is called source tilt, and the second step is called lens alignment. The source tilt adjuster will adjust the angle of the electron beam as it comes down the column. If the angle is too far off to the side, you will not get an image on the screen. For example, if I grab the source tilt adjuster and move it sideways, eventually I completely lose my image. If I bring the source tilt back, my image returns. Now, there is a more accurate way to establish the source tilt. Instead of just moving this around looking for an image, we're going to activate a special mode in the software called crossover mode. So I'm going to click on crossover, and this causes the microscope scanning to change and show a green X on the screen, and we should see a spot somewhere on the screen as well. If you cannot see the spot, simply turn up the brightness and contrast until the spot is visible. Now, unfortunately, there's no way to magnify this image, but what we can do is we can change the microscope UI from quadrant view to full screen view. This is done by going to the window drop-down and selecting the single versus quad image mode selection. The keyboard shortcut for this is F5. In the full screen view, it is considerably easier to see functions like this. Now, the green X, which is added in the software, represents the center of the optic axis for the electron column. Wherever the bright spot is, indicates the location of the source tilt, and we want to adjust the source tilt to the adjuster to move the center of the bright spot onto the center of the green X. So I'm simply going to click on the source tilt adjuster and move the mouse to reposition the center of the bright spot on the green X. And that's all we have to do. We then turn off the crossover button and we are back to our normal imaging mode. Keep in mind that if you adjusted the contrast and brightness in crossover mode, those settings translate back to the regular imaging mode, which is why my brightness and contrast are way too high now. So I can make some adjustments and bring those values back down. The second part of column alignment is called lens alignment. The lens alignment will shift the X and Y position of the electron beam so that it passes through the center of the objective lens. This primarily is done to improve resolution of the image. In order to find the lens center, we want to turn on the lens align button. This will cause the system to start wobbling the lens strength, which will result in the image going in and out of focus. If the electron beam is passing through the center of the lens, the image will not appear to move, simply go back and forth in focus. If the lens alignment is not correct, so I'm going to mess up the lens alignment now, the image will appear to translate in some direction. In this case, it's moving on an inclined angle from left to right. I want to change the lens alignment to the adjuster to try to minimize the motion in the image. If I move this adjuster to the left and to the right, I can add or subtract to the horizontal component of the lens wobble. So in this case, I'm moving only the horizontal component, and I have now caused the lens wobble to become only in a vertical direction. I can now grab the horizontal line and move this up and down, and I can try to remove the vertical part of the wobble. Usually this procedure has to be iterated several times. So now by removing the vertical wobble, I now have a little bit of horizontal wobble again. So I'm going to go back and I move the vertical line left and right and try to minimize the rest of that wobble. If your magnification is at a very low value, the image will appear to rotate when the lens align button is turned on. This can be very, very distracting. The only solution to remove the image rotation is to increase the magnification. So if I turn up the magnification to a suitable value, the rotation of the image stops, and I should only see the translation of the image caused by the lens misalignment. So once the lens alignment is finished, I can then turn off the lens align button, and the microscope will return me to the magnification and scanning conditions that I was using before I turned on lens align. The final steps to getting a good image are going to be to adjust the focus and the astigmatism of the microscope. To do this, I'm going to move to a slightly different area of my sample. I'm going to double click on this region, and I'm going to increase my magnification slightly. Now, with my current conditions, we can see that my imaging parameters are not very good. I need to adjust focus. I need to adjust astigmatism. I'll start with focus, and I can change focus by turning either the fine focus knob or the coarse focus knob clockwise or counterclockwise until my image improves. So as I pass through focus, the image gets better and then gets blurry again. It's generally a good idea on SEMs to smoothly wobble the focus knob back and forth through focus several times to try to figure out where is the optimum value. Try to avoid turning the knob very, very small increments. It's very inefficient. Now, if I have astigmatism, let me zoom in on a round particle here. If I have astigmatism, as I pass through focus, round objects will distort on two different orthogonal directions. I'm going to mess up the astigmatism a little bit more here to emphasize this fact. Okay, so as I pass through focus, I'm going to use the coarse knob here. What we see here is that I have relatively round objects on my sample, and on one side of focus they are elongated in this direction, and on the other side of focus they are elongated in this direction. The focal point is where these objects are not elongated in either direction. This can usually be found by simply wobbling the focus knob back and forth and trying to establish the position where the objects change shape. I would estimate that this point is close to focus. You can see that these round objects are approximately round, even though the image quality is not very good. Once you think you're at the focal point, the next step is to remove the astigmatism. This is done using stigmators. There is an X and a Y stigmator adjuster that can be controlled by the mouse in the beam control menu, or there's an X and a Y stigmator knob on the MUI panel. I prefer to use the knobs on the MUI panel. So I'm going to start with one knob. It does not matter which one. in this case X, and I'm simply going to turn it one way and look for the image to get better, and then turn it the other way. And again, just like when you're adjusting focus, we're trying to find the point where the image looks the best. I will then do the same thing with the other stigmator knob. Turn it one way, the image gets worse. Turn it the other way, the image gets better, and then worse, and then I'll go backwards, and I'll try to find the point where the image is best. Now, you may have to repeat this process several times to get a good image. The general procedure is to adjust the focus, and then one stigmator, and then the other stigmator, and then go back and repeat. Focus, stigmator, stigmator, focus, stigmator, stigmator. Once you think your image is good, you can always turn up the magnification and look for smaller and smaller features to try to improve your focus. In order to assist with the ability to see features on the sample, you may find that you have to adjust your contrast and brightness as you go, and you may have to adjust your scan speeds. On the Nova software, the scanning speed is controlled by this dwell time adjuster up in the toolbar. If I click the left arrow, the scanning goes one step slower. If I click the right arrow, the scanning goes one step faster. You may find that faster scanning can be useful, or slower scanning could be useful depending on your situation. If the scan speed is very slow, your signal to noise is much better in your image. However, you will have to wait for the image to refresh to see the results of your focusing. One way to get around this problem is by restricting the scan area to a small area. This is called reduced area mode. If I activate the reduced area mode, I can position a small scan window on top of a feature, and this allows me to then use a longer dwell time but still get a reasonably fast scan refresh speed, which helps with focusing. So by looking at this small area, I can then try to adjust my focus and astigmatism as I need to. And I should probably try to find some smaller features. This feature is a little bit large. Let's use some of these little nanoparticles here. These will probably work better. Okay, now this is about as good as this microscope is going to perform with these current conditions. The reason that these images look rather blurry is because I'm exceeding the resolution limit of the microscope with these settings. However, I normally would not take images at 150,000 x mag with these settings. Normally, I would be using magnifications more like this, in which case the microscope is going to perform very well. So now that I've fixed my focus and astigmatism, as well as my source tilt and lens alignment, I'm now ready to take a picture. There are three main ways to acquire images on the Nova. The first way is to simply slow down the scan speed until the image quality improves. I would say this looks fairly reasonable, and then hit the pause button. If you hit the pause button once, the microscope will complete its current scan, and then it will freeze the image. If I want the image to stop immediately, I can hit the pause button a second time and the image will stop scanning immediately. Once the image is paused, as shown by the pause indicator in the top left, I can then go to File and click Save As or Save, and I can save the image to a location on wherever I want to go. On our system, we would prefer that you save your images to the linked drive, which is located on the support computer, which is the computer to the left of the microscope computer. For this demonstration though, I'm just going to create a folder in this drive. So I'm going to go to temporary data. I'm going to say new folder, demo. We'll select this, and I will change this to demo image. So when you're saving your images, your file name goes here. This is your usual Windows file save window. You have two options in the bottom left. You can choose to save the data bar as part of the image or to turn it off. And you can choose to save an overlay graphic or don't save it. There are 5 different image formats that you can use to record an image. I strongly recommend you use one of the TIFF formats. The TIFF 8 and 16-bit are grayscale only formats and differ in the number of channels available between black and white. An 8-bit image has 256 channels between black and white. A 16-bit image has 2 to the 16 power channels between black and white. The 16-bit image is much more useful for any type of image processing, Photoshop, or digital measurements that you may want to do later. The TIFF24 format is a color format. It allows you to save color overlays in addition to the grayscale component of the microscope image. However, the grayscale component in a TIFF24 image is similar quality to the TIFF 8-bit grayscale image. Therefore, the TIFF16 is still the best quality image format that can be recorded on this microscope. The bitmap and the JPEG images are not high quality images. They're more of a legacy image format that's used to make very tiny image files. However, that is not really a concern anymore because we have almost unlimited hard drive space. I believe that the reduction in image quality makes these files almost useless on this microscope. So I'm going to choose the 16-bit TIFF image and click Save. Now, the second way to acquire an image is to use a function called the snapshot. This is a camera icon up here in the toolbar next to the pause button. If I push the snapshot, the system is going to acquire an image using a preset scan speed. Generally, the snapshot is configured to be a very quick scan. The third way to get a scan or to acquire an image is called the photo preset. It's activated by going to the scan dropdown and choosing photo, or by selecting F2 on the keyboard. So if I hit F2 on the keyboard, this will activate the photo preset. Now the snapshot and the photo preset are going to set the microscope up to certain scan speeds, a certain image resolution, and acquire the image for you. In this case, the photo preset is activating a 30 microsecond dwell time and is taking a picture with 1024 by 884 pixels. There can be other functions enabled as well that can be mapped to the snapshot and photo preset, which I'll show you in a second. Now, I don't want to save this image, so I'm going to just simply hit cancel. If I want to change the snapshot or the photo preset conditions, I need to go to the scan drop-down menu and go to the preferences option at the bottom. This brings me to the scanning tab within the preferences menu. This will show a list of dwell times, which are your live scan speeds. Right now we're using a 300 nanosecond live speed. If I click the right arrow, it will go to 100 and then 50. If I click the left arrow, it will go down through this list. Now these scan speeds can be changed to suit your purposes. If I, for example, I want a 500 nanosecond live scan speed, I can simply choose one of these values, highlight it, and change it to 500 nanoseconds and hit enter, and then hit apply, and now I have a 500 nanosecond speed. So if I click the right, it'll go from 3 to 1 to 500 and 300 and so on. The two cameras on the right hand side of this list are the snapshot and the photo presets. The top camera is always going to be the snapshot. The software requires the snapshot to be a faster speed than the photo preset. So if I choose the snapshot button, or the snapshot camera icon, I can then see all of the settings that are used when I push the snapshot. So in this case, it's doing a 1 microsecond dwell. It is not doing line integration. It's taking 512 pixel by 442 pixel images. It's doing 1 frame, so no frame integration. It's acquiring an 8-bit mode, and then at the end of it, it is going to pull up the file save window for me. Feel free to change these settings to whatever you like. It's generally a good idea to always check these values when you start a microscope session so that you can undo any changes that the previous user may have done. I'm going to change my dwell time to 3 microseconds. I'm going to change my resolution to 1024 by 884. I'm going to change my acquisition to 16-bit acquisition, and I'm going to disable the save as. I'm going to set it to simply none and hit apply. So now when I hit the snapshot, I will get those settings to get my image. And if I want to change my photo preset, I can go back to Scan Preferences, choose the photo preset, and I can choose different scan speeds for this one as well. Keep in mind that the software only lets you select scan speeds that are available in the live scan list. If you want a different scan speed for your snapshot or photo icon, you have to modify one of the live scan speeds first. To demonstrate, let's say I want a 50 microsecond scan speed. I only have 10, 30, and 100 available here. However, if I choose one of the scan speeds that I'm not going to use, and I change this to 50 microseconds, and hit apply, I can now select my photo preset and pick 50 microseconds. And just like before, I'm going to change my acquisition to 16-bit, and I'm going to leave the action as save as this time. And I hit apply, OK. So now when I hit F2, I get a 50 microsecond scan at 1024 pixels. While acquiring images this way, the functions of the pause button are still the same as in live scanning mode. If I hit pause once, the image will complete its current scan and then freeze. If I don't want to wait for this image to complete, I can hit pause again and it'll freeze the image. And then pause a third time goes back to live scanning. Other features that we can try, if we go back to Scan Preferences and choose the snapshot, we can look at doing line integration. So instead of doing a single frame, let's do a 300 nanosecond dwell, and let's hit apply and say OK, and let's take this image. Now a 300 nanosecond dwell time is a relatively fast scan, so the image looks rather noisy. However, if I invoke line integration, I can cause the SEM to repeat every line a certain number of times. Let's try 8x line integration. This means that every line will be repeated 8 times and the resulting signal will be summed up, which will reduce noise. However, it will appear that the image is scanning slower. However, you see that the noise is reduced. Now, I need to check. I think my other camera just shut off. Yep, it did. Oh, my battery's running out. All right, well, we'll proceed without that camera. We don't need it. So that's line integration. I can also do frame integration. So instead of choosing line integration, I can choose frame integration as 8x. The difference is that frame integration acquires the complete image 8 times and adds it together instead of acquiring each line 8 times in one scan. So in frame integration mode, the image will start out as a black image and it'll get brighter as it accumulates more frames. The signal to noise gain for either line integrate or frame integrate should be about the same. However, there will be subtle differences in the scanning. So please try either method to see what works for you. However, if your samples are conductive and stable, it's generally a good idea to do a single slow scan on the Nova. It generally produces the nicest image. So what we should do now is let's take a look at how to activate the high resolution objective lens. As I mentioned, our current conditions with the SEM do not allow us to easily see these small features. We can turn off the low resolution objective lens and enable the high resolution objective lens, which will give us much, much better clarity on these small features. The way to change the lens modes is by using this icon up here in the toolbar. Now, if I simply click on the icon, it will switch to the high resolution objective lens. However, if I click the down arrow, the user interface will show me that I actually have 3 different lens modes. Now, there are only 2 objective lenses on this SEM. There's the low resolution lens and the high resolution lens. The low resolution lens is also referred to as mode 1 field free mode. The high resolution lens is called mode 2 immersion mode in the software. These are two physically different lenses. Mode 3 EDX mode is a hybrid mode that uses both objective lenses at the same time to act as a filter for doing X-ray analysis. For imaging purposes, the resolution of mode 3 is very similar to mode 1. So I would not recommend that you use mode 3 for imaging unless you have a very specific circumstance. And maybe I'll make a video about this in the future about when mode 3 is a good idea and when it's not. But generally, this is for doing X-ray analysis, not for just imaging. Now, when I switch to mode 2, the software is going to change several things for me. The first thing that's going to change is that my detector is going to change from the Everhart-Thornley detector to the through lens detector. So if we go look at our detector tab, we have two different detectors available, the ETD detector or Everhart-Thornley and the through lens detector or TLD. I can use either detector when I'm using the low resolution lens. Generally, the ETD detector gives you the best image, especially at low magnification. You see the TLD detector shows a relatively small bright spot in the center of the image, whereas the ETD detector gives a much nicer view. However, when I switch to the high resolution lens, the software is going to force me to use the TLD detector. I have no choice in the matter. The other thing that's going to happen is because I'm switching to a different objective lens, my focus, astigmatism, and lens alignment are all going to be changed. Technically, the source tilt does not change on the Nova when you switch between the low resolution and high resolution lenses. However, it's always a good idea to double check this. But if you've already aligned the source tilt, you don't have to do it again. So let's go to switch to mode 2 immersion mode and let's see what happens. Now, just as I predicted, our focus and astigmatism are bad. Our brightness and contrast are no longer valid because we're using a different detector, the TLD detector. And our lens alignment's probably bad. So let's start out by aligning the column again. So we'll go to the source tilt, turn on crossover mode, and we can see that the source tilt is the same as it was before, but it's good to check. Next, we're going to turn on the lens alignment, and we're going to double check that our lens alignment is good. Now in this case, the lens alignment looks pretty reasonable, but it may or may not be. So just like before, if we have a lot of misalignment issues, we want to adjust the lens alignment to get rid of the motion in the image. And that looks pretty reasonable. Let's turn off lens alignment. Next, we want to adjust our focus. And we can see already that we have much better resolution than we did before. We're going to adjust our focus, and then we're going to adjust our astigmatism using the stigmators. Now, if we want to look at some very small features, let's go find some small carbon particles on this sample. And let's zoom in here a little bit, and we can use our reduced area scanning to fine-tune our focus and our astigmatism. All right, and at this point, we're at a fairly high magnification for this microscope. And you can see that the image is actually drifting a little bit. This drift is mainly caused by instabilities in the electron lens. This will normally go away after a few minutes after you switch into the high resolution mode. However, if this type of drift persists, it may indicate a problem with the microscope or a problem with your sample mounting. For the purposes of this demonstration though, we're going to ignore this drift. And I'm just going to take a crude image here and hit pause. Now, if we want to measure the size of some of these features, we can go to the fourth tab, the image processing tab, and we can choose different types of measurements. And if I put a circle measurement around this feature and turn off the tilt correction, we can see that this particle is approximately 20 nanometers in diameter, maybe a little bit smaller. If I look in the background over here on the left side of the image, I can see features that are probably definitely less than 10 nanometers, maybe somewhere between 5 and 10 nanometers in diameter. Let me see if I can get a little bit nicer image of those. All right, so the perimeter of these are a little bit blurry, but we can see that they exist. And I would say maybe 6 to 7 nanometer diameter. The point of this demonstration is to show that without too much effort, you should be able to resolve features below 10 nanometers in diameter on the Nova using fairly standard beam conditions. 5 kV, 0.4 nanoamps, 5 millimeter working distance using the high resolution lens. If you find that it takes more effort than what I've shown to get good images, please come ask for help from the staff, because it probably means that you're missing a step or there's something wrong with the microscope. Now, some other things that we can do to show the capabilities of the system are to play around with the detectors. Now, this particular detector, the through lens detector, is a very powerful detector because it has an electrode on it called the suction tube. The suction tube is used to either pull in low energy secondary electrons or to reject them from the image. And this allows us to operate this detector in secondary electron mode or backscatter mode or a couple other modes called charge reduction, downhole visibility, and custom mode. Now, the advantages of this are not immediately evident until I make some changes to my imaging conditions. I'm going to change to 3 kV accelerating voltage, and I'm going to change to a slightly higher beam current of 1.1 nanoamps. Now, because I made a change to either the voltage or the beam current, I have to realign my microscope. So I go back to beam control. I'm going to turn on my crossover button and check my source tilt. Okay, and then I'm also going to check my lens alignment. And I can see I have a little bit of lens misalignment here. So I'm going to adjust my lens alignment. Now in this case, you see I'm grabbing this little green crosshair in the middle of the screen. This is the same thing as grabbing the lens alignment adjuster on the side. And that looks pretty good. And I'm going to make a fine-tune adjustment to my focus and astigmatism. Now, I wouldn't expect my resolution to be quite as good with these conditions because I lowered my voltage slightly and I went to a higher beam current. But what I'm trying to show you here is what these detector modes can do. So I'm not really worried about resolution at the moment. Now, in this image, we are using secondary electron mode. Secondary electron mode means that the suction tube is positively biased and is actively pulling in the secondary electrons produced when the beam hits the surface. There are also backscatter electrons produced when the beam hits the surface. The difference between the two is that secondary electrons are very low energy and are very easy to deflect using electrodes like the suction tube. The backscatter electrons are very high energy and are difficult to deflect with these electrodes. The important thing to keep in mind that an image in secondary electron mode is always composed of a backscatter component and a secondary electron component together. If I change my mode to backscatter mode, what happens is the suction tube goes to minus 50 volts, which acts to exclude all electrons with energy below 50 eV. Now on the Nova, changing the suction tube voltage does affect your focus slightly. So when I get my focus back, what we see is now a backscatter image. So The secondary electron mode is the secondary and backscatter signals added together. The backscatter mode is just the backscatter electrons. So the secondary component is now filtered out of the image. Now the advantage of a backscatter image is that it shows you where the different materials are on your sample. Now this particular sample has carbon and platinum on it, which are extremely different atomic number. So there's a very, very big difference between the carbon material, which appears dark, and the platinum material, which appears bright. But generally in a backscatter image, your contrast is proportional to the atomic number squared. So bright areas will be higher atomic number, dark areas will be a lower atomic number. And now I can see in my backscatter image that I have carbon, and there's some small platinum nanoparticles buried in these carbon materials, and the background is platinum. If I go back to my secondary electron image, secondary electrons typically carry topographic information. The only reason we would see any contrast from the different materials would be from the backscatter component that would also make up part of this image. However, the secondary electron signal is substantially stronger than the backscatter component, which is why the secondary electron image looks more topographic in nature, and it's much harder to tell that all these objects on the surface are a different material. However, it's easy to tell that they are all bumps that protrude from the surfaces. Now, another mode that we can use instead of using just secondary and backscatter mode is what FEI calls charge reduction mode. Now, let's go to an area of this sample that's a little bit insulating. How about this stuff over here? So this material is charging up a little bit. As we scan over it, you can see there's a lot of these horizontal flares. It looks kind of cloudy in nature. It's difficult to see what's going on. Not the greatest. The idea with the charge reduction mode is that it sets the suction tube to 0 volts, and this is supposed to help keep charge from being a part of your image. The issue is that the software engineers did not set this value to where it needs to be, so 0 volts is actually fairly useless for doing charge reduction. The correct way to do this is to put the software into custom mode. So I'm going to go back, I went back to secondary electron mode, and then I'm going to go to custom mode. And in custom mode, you can now have free control over the suction tube bias. So if I set the suction tube to 50 volts, I'm now in the identical condition as secondary electron mode. If I set it to negative 50 volts, I'm in the same condition as backscatter mode. And what I want to do is I want to slowly turn the suction tube negative. And as I do this, we should see that the charge in the image is dissipating. So when I hit 0, I will start to throw away signal. So we keep going negative, and I think I chose a poor area for this demonstration. Let me find a better area. I'm too close to these large objects. They're causing problems. All right, this is a better spot. Okay, so again, I go into, I start turning the bias down, and as we go lower and lower in bias, we should see that that charge is reduced from the image. Now, when I get to negative 50 volts, I'm in the same condition as backscatter, but you may find that you have to go substantially further than minus 50 volts. Sometimes you can get rid of the charge by going to minus 10 or minus 20 volts. Sometimes you have to go all the way to the limit of the tool to get rid of the charge in the image. Now, in this case, I've maxed out the suction tube at minus 252, and I still have a little bit of a charge artifact, but I can now see what's going on in this area of the sample. I can see that there's actually little platinum particles embedded in this graphite material, which I couldn't see with the charge. Now, if I slow down my scanning speed to try to get a better image of these things, I can cause more charge to appear. So the better way in this case is to use a fast scan speed and use frame integration. So I'm going to go to scan, preferences. I'm going to change my snapshot to 100 nanoseconds, and I'm going to do 32 frames of integration and hit apply. And now if I hit snapshot, I will get an integrated image, which doesn't look too bad. It looks like I'm a little bit out of focus, but not too bad. Let's see if we can fix that focus a little bit. So, focus and astigmatism. Maybe turn our contrast up a little bit, and let's try that again. All right, pretty cool. So that's the custom mode on the TLD detector. Very useful for getting rid of charge. Now, it's not a magic solution to all samples. I can't put a piece of glass into this microscope and image it with this mode. But for semiconductor type materials or small areas of insulating materials, it works pretty well. Also, keep in mind the backscatter mode is really great for looking at different areas of your sample that have different compositions. And then the secondary electron mode, which is your normal imaging mode that we're going to use. Now, if we want to improve our resolution a little bit, what we should do is we should go to a smaller beam current, and we should also decrease the distance between the sample and the lens. The software will let you go all the way to 1 millimeter from the lens, and as you get closer and closer to the lens, your resolution improves. However, it gets harder and harder to safely move your sample around. You lose the ability to tilt and rotate safely, and your depth of focus is significantly reduced. However, let's just say we want more resolution on this sample. So the first thing I'm going to do is go to my navigation tab, and let's bring the stage up to 2 millimeters. I'm going to say 2 and hit enter. Now, as I bring the sample closer to the lens, you should see that this icon for the link has changed to a red circle. That means that the software thinks I could do a much better job of linking the working distance to the z-axis. So if you see the red circle, what we want to do is to adjust our focus again, get our image looking good, and then update this link. So originally I thought I was at 2 millimeters. I'm actually at 2.09 millimeters. Not a really big deal. But anytime you see the red circle show up on this icon, just make sure you're in focus again, and then push it, and that updates the value for the z-axis. And let's drop our beam current down. I'm going to take it down to 68 picoamps. And because I changed the voltage or beam current, I have to realign the column. So we'll go back to beam control. We'll go to the crossover button. We'll check our source tilt. And then we will check our lens alignment. And so we got a little bit of a lens alignment issue here. All right. And lastly, let's find some of those small nanoparticles again, and we'll see if we can get a little bit clearer image of those things. So I'm going to use my reduced area scan. I'm going to adjust my focus, adjust the astigmatism, and let's see if we can do a little better than that. All right, and let's slow our scan speed down. We'll just use a nice slow scan, F2, that activates my photo preset. Now, you should hopefully notice here that the top and bottom of my image are not in focus. This is because my depth of focus is very, very limited. I'm focusing on the step in the middle of the sample, and there are other features at differing heights that are out of focus. So these really high resolution conditions when you're close to the lens are better served with flat samples than bumpy samples. But this looks pretty nice. I'm not going to sit and wait for this to finish all the way, but again, you can see this feature down here on the bottom of the screen is quite out of focus, even though the middle is in focus. Let's see if we can find some of those small particles. Here's some. So at 5 kV and at 0.4 nanoamps and 5 millimeter working distance, I could see features that were about 7 nanometers in diameter, but they were a little fuzzy. Now let's see if I can do any better here with these conditions. Now I'm talking while I'm taking my images, which is not a good idea. You can see the microscope is picking up the vibration from my voice. So if I be quiet for a couple seconds to at least get a particle in the field of view, and then we can try to measure this, and let's see if we did any better. Well, it looks like there was a relatively small one right there, about 10 nanometers or so, 10 nanometers. So about the same feature size, but I would argue that this image is slightly clearer than the 5 kV image. Notwithstanding all the vibration from the shaking, but what we could also do is, instead of going with that really slow scan, we could go a little bit faster scanning here. Not too bad. So just like before, we can see features that are below 10 nanometers in size. And again, this gets into more of a personal opinion, but I would say this image looks a little better than the 5 kV image did. You could try to measure the resolution of these images, but at the end of the day, we usually don't do that for all the pictures we take. So that's a quick overview of how to use the Nova, how to set it up for SEM imaging. So let's go ahead and shut the tool down. So to do that, we're going to go to the beam control tab, and we're going to hit the beam on button, which will close the column isolation valve. We can pause the scanning, and then we just hit the vent button. Now, when you hit the vent button, the stage of the microscope should drop to the minimum height. If it doesn't do that, you would want to go to the navigation tab and type in 0 for Z, and also for tilt if you happen to have tilted the stage. But we have the software configured to lower the stage automatically. So now we have to wait a couple minutes for the chamber to vent. Then we can go ahead and open the door and take the samples out, close the door, hit the pump button, and then we are all set. Make sure that the chamber is actually sealed up and pumping before you leave. Make sure you didn't leave the door propped slightly open. Make sure that there's no dust or dirt or hairs or anything blocking the door seal. So we've had that happen in the past. And then we can log off in our billing software, and the system should be ready for the next user. So I hope you appreciated this movie. I hope you learned a little bit from it, and please let me know if you have any questions. Thank you.